Okay, so going over simple linear regression today. Did anybody have any questions on anything before we start looking at this activity? All right. So simple linear regression is one of the most important methods this semester. In my opinion, the most important model and method we cover this semester. Actually, I think in all of statistics. A lot of different models and methods can be boiled down to a fancy way of forming a linear regression model. Or more complicated methods can sort of be thought as clever ways of using a bunch of linear regressions. So if you can have a good understanding of this, it opens up a lot of statistics, and yeah, you can do a lot of things with it. See, I don't talk about it in the activity here, but the one sample t-test, the unpooled or pooled two sample t-test. One of the two sample t-tests, one-way ANOVA, two-way ANOVA, those are all actually specific cases of regression models. Like you can formulate a regression model that's equivalent to those results. So it's kind of like if you, you know, that phrase, it's like when you have a hammer, everything looks like a nail. I think that's the right phrase. So it's kind of like this is the hammer. You can do everything pretty much with linear regression, or many things at least. So that makes it a very useful tool anyways. Okay. So we'll be talking about the simple linear regression model itself, the model assumptions that we need, which will look familiar considering what we've covered for ANOVA. And that's again because ANOVA is a specific case of a regression model. So actually the way we check the assumptions, very, very similar. We'll talk about how we can interpret some of the model output that we get from SAS. And then what's kind of fun is you can get predicted values, right, from regression models. So we'll look at briefly how you can do that. You all have seen linear regression a little bit, hopefully in Stat 215. I know it's kind of brief, but you do see it somewhat. Yeah, it's like to show, let's see if I can get it pulled up here. Oops. Is anybody following March Madness right now in NCAA basketball? That's always fun, right? So I used linear regression for fun to predict outcomes of games. I didn't use SAS, I used R, but you could do SAS, use SAS for this. So let's see. Yes, over years. This took years to I made this from scratch essentially, yeah. But you can, to zoom this a little bit. Yeah, maybe it will. Okay, but you can, for example, okay, so margin of victory model. So here's very essentially a linear regression where yeah. Okay, so like when Michigan State played, who did they just play? Marquette, yeah. Okay. So we could use this to, we could use linear regression. Oh, Marquette was the favorite, that's why. It's a little bit blurry, but use linear regression to get a prediction beforehand about the game based on previous information about the teams. My model was not gave like Marquette 58%. Pretty happy with it. Michigan State won, so I think 58% seems reasonable. Yeah, this is like sports. You know, predictions for sports is one very common use of linear regression. Yeah. Yeah, definitely. So a lot of people who are like, some people make a lot of money off of forecasting the results of games. And yeah, Vegas, from my understanding, they set the betting lines based on like how much people are betting on each side, which is like the gold standard, because like in the aggregate, it's known that people are more accurate if you like sum across like many people's predictions versus anyone's like individual model. But yeah, kind of fun. That's like one fun example of how you can use linear regression or predictive modeling. But of course, many other contexts as well, like development of novel treatments in the pharmaceutical industry. You know, Target will use it to try and maximize how much you're spending at their store, right? So lots and lots of different cases where it's useful. So simple linear regression being the most fundamental of regression models, involves a single quantitative response variable, which is commonly denoted by y, and a single explanatory variable denoted by x. Okay. So here's where it's paying off, where we looked at the more complicated version of the t-test and the ANOVA, where we had y is equal to like a function of x's. That was a linear model simulation. And now that same syntax and the way we do it carries over here. So simple linear regression relies on this assumption of a straight line relationship between x and y. And notably, it's called simple linear regression just because there's one predictor, x. That's what makes it simple. It's not that it's a not complicated model. For some reason, the naming is just simple means one predictor. Okay. So some other examples, yeah, besides basketball or the other things I mentioned, you could, and people do, try and predict stock prices, right? This is a very difficult problem to do, but people try. So you can use things like trend in the gross domestic product, probably the previous month's stock price. All of those are important factors probably in predicting next month's stock price, which a lot of people try to do for buying and selling stocks to make money, right? Like I mentioned, for drug development in the pharmaceutical industry, okay, so maybe your outcome is like the blood pressure of a patient, okay, and you want to develop some new treatment, or you have a new treatment that you think would work in lowering people's blood pressure, help them live longer, happier lives. Okay, so we could use linear regression to explore the relationship between using our new treatment and people's blood pressures. Okay. Right, how long a car component will last based on the number of miles on the vehicle. Okay. So if anyone's had a vehicle, you're aware that the longer you've had your car, the more miles you put on it, more likely it is something's going to break, right? So when people are like designing these cars, like engineers, they likely have some type of predictive model in which they estimate how long the car part will last until it breaks. And so you can imagine like the duration of the warranty is very purposely set at a certain amount of time because they probably predict stuff will start to break right at that point or shortly after. Okay. So they can make a lot of money or lose a lot of money depending on how accurate they can predict how long the car part will last, right? And then, yeah, like I mentioned, Target or like Meyer does this, right? Like if you're on social media, which probably everyone is, you see a lot of ads, right, that companies pay for. And so many companies probably explore the relationship between how much they spend on advertising on social media and then how much revenue it generates. Okay. Another important use case where you can say, like, oh, given every $10 we spend on ads, we expect this much more in revenue. And so that's helpful to evaluate marketing strategies, right? Okay, so lots and lots of different cases for linear regression. Talking about terminology, so we refer to y, the response variable. We refer to y as the response variable, which is the quantitative variable that we're interested in predicting, or just the outcome of interest very generally. It's not always predictions that we're trying to make using linear regression. Sometimes it's just understanding relationships between x and y. And x is the explanatory variable, or in regression modeling, it's more commonly just referred to as a predictor variable. Okay. So let's start. This is a longer activity. I don't think we'll finish it today, but we're gonna see how far we can get. So looking at these examples up here for A, oops. You can say what each of the response and explanatory variables are. Okay. So let's say A, for part A, or example A here, what is the response variable y? Right, the monthly stock price. Mm-hmm. And what is our predictor variable in that case? GDP. Yep. Gross domestic product. All right, what about B? What's our outcome of interest there? Yeah, it gives the example of blood pressure. So we'll say blood pressure. And then what's the predictor variable there? Dosage level, yeah. Car component. What about the car example? What's our response? Yeah, how much longer a car component will last? Mm-hmm. And then explanatory variable. Yeah, number of miles on the vehicle. All right, and then the last one. What would be our outcome of interest there? Yeah, sales revenue. And I think we said in dollars. and then how much we spend on social media advertising, right? So those are just a few examples. The reason it's important to differentiate the response and the explanatory variable, when you code this up in SAS or another programming language, you have to tell SAS which one is the response variable and which one is the explanatory variable. It doesn't know automatically. So it's important for you as the statistician or programmer to be able to understand that. Okay. Any questions on those? Okay. So the theoretical or assumed simple linear regression model is given by this equation, which again maybe looks a little familiar based on how we've talked about the ANOVA model and the t-test. So we have our response variable on the left. So let's maybe look at like the blood pressure example. Okay, so this is each patient's blood pressure. We have it's equal to a linear combination of x here, we call it. So an intercept plus a slope times x plus an epsilon term here, which is the error or residual term. So like, yeah, describing what these pieces would represent in the blood pressure example, this would be y would be each individual's observed blood pressure. Beta naught, the intercept term, would be the true average blood pressure of all people. So sort of like we talked about before with like ANOVA, you like build up a person's observation that you saw by first starting with the most average person. Like we start with their most average blood pressure. And then if we know the dosage level of our treatment that they were on, we have some number times that dosage level affects their blood pressure. So maybe if higher dosage levels decrease their blood pressure, this would be a negative effect for that. And then the idea is that even people with the same dosage of our treatment, they don't necessarily have exactly the same blood pressure. There's individual differences person to person. And so this epsilon term captures that individual uniqueness, that person to person variability, even at the same dosage level. Okay. So that's essentially how the linear regression model works here. And notably, this theoretical model, like the wording, how I said that is very careful. This is the true average blood pressure of all people, which is a number we'll never have. We don't know that number. And this beta one represents the true effect of our treatment, of the dosage level of our treatment, which again, we'll get a sample of data and we can estimate that, but we don't know the actual true value unless we had data on every single person in the world that we're interested in. So collectively, beta naught and beta 1 here, beta 0 and beta 1, define our straight line relationship between x and y. And it might look familiar, like from high school, I think calculus class, you learn y equals mx plus b, right? You also learn that? Yeah, that's how it was when I was in school. So this is the equation for a straight line, right? So this is the same for linear regression. We just use slightly different notation, and the order of things is swapped a little bit. It's kind of like B is the beta naught, M is the beta 1. And then the reason there's the epsilon term is because okay, so like if you plot this out and you have x and you have y, okay, y equals mx plus b tells us that there's like a straight line relationship like this, which, yeah, maybe is the case, but often there is, when you observe points for a real data set, it looks something like this, okay? In which case, the points don't fall exactly on the line. There's like some error or discrepancies between them. And so that's what the epsilon describes, this distance from the straight line up to the observed point here. Okay. So very similar to y equals mx plus b, just a little bit more going. Okay. So this theoretical model, or this assumed model, this is what we're assuming holds true in the population here. When we use a linear regression model, essentially what we're going to do is try and estimate these two beta terms so that we can get an estimate of the true straight line relationship between x and y. So we end up with this estimated regression equation, which is what we use to make predictions or to describe what we think the relationship between x and y is based on our data set. So we have y hat, our predicted value or estimated response value is equal to the estimated intercept plus an estimated slope times x. And what do we notice about this equation compared to the assumed one or the theoretical one, besides the hats? Yeah, there's no epsilon, right? So that's because this is y hat on the left side. It's what we predict, not the actual y value here. You could write like the actual y is equal to beta hat 0. I'll just write b hat 0 plus b hat 1 times x plus e. You could write like the estimated regression equation that way. But honestly, it's just like conventionally people don't write it that way. So they write it this way without the residual term. Right. Yeah, so based on a given data set where it would look something like, okay, so if we have an observed data set, it would look something like this, where we have like x, and then we have our y, okay, and then, you know, maybe we have like a 1, we see it's what we got for the first observation, see 2, and then x is 0, like maybe this is dosage level, and then it's not very reasonable blood pressure level, I guess, but something like that. 0 again, and then 2, okay, and so on. Okay. That's like how a data set might look for linear regression. You have this table of numbers for x and y, and then using that and actually using calculus and some derivatives, we end up with a single number as our estimate for beta naught hat, the slope or the intercept here, and another number estimating the slope, beta 1 hat. based on all these numbers in the table. We can interpret those estimates that we get. Beta naught hat in particular is the expected value of y given that x is 0. Okay. And another way to think about it is that beta naught hat is the predicted value for y when x is 0 for our model. Okay. You can see that up here. If you make x equal to 0, y hat is just equal to beta naught hat. Okay. And for beta 1 hat, the estimated slope, we generally interpret that as for every 1 unit increase in x, we expect y to increase or decrease by this amount. Okay. And I have absolute value of beta hat 1 here. This is similar to confidence intervals, how we've talked about in interpretations. We don't like to use negative numbers. So if it's like -5, you'll just say decrease by 5. And if it's +3, you'll say increase by 3, rather than using negative numbers in interpretations. Okay. All right. So, okay, would we expect all right, let's think about the slope, which describes the relationship between x and y for each of the 4 scenarios up here. Okay. So we already talked about what x and y were. So for the first one, we said x was GDP, y is the stock price of some typical stock next month. If GDP goes up, what would we expect to happen to the stock price next month, maybe? Probably also go up. I mean, there's going to be a lot of situations where it varies, but generally that's the idea here. So what would we say about the slope? It's positive, right? If the variables tend to go up with each other, then it would be a positive slope. But thinking about that more, so if the GDP goes down, if the GDP is like much lower this month, what would we expect about the stock price next month? It would decrease. So then would we think the slope is positive or negative between the two variables? It's a little bit tricky. Let's maybe draw it out real quick. Okay, so we've got our scatter plot here, and then we said x was the GDP. Okay. And then we said y was the stock price. Okay. And let's say let's see how this would look. Okay, we said as GDP goes up, so as GDP increases, the stock price would tend to increase as well. And then linear regression involves estimating this line of best fit through these data points. Okay. So this, we decided, has a positive slope. It's sloping upward, right? Looking at the same chart, we were thinking about then, well, what if GDP is decreasing? Okay, so maybe like, actually what we're meaning by there then is moving from right to left on the plot. So GDP would be going down. Does that change the slope of the line describing the relationship? No, it's actually still the same. So if they go down together, that indicates a positive slope. Going down together is the same as consistently going up together in terms of linear regression is concerned. So still a positive relationship there. Okay, what about the next one? So we have dosage level, and we're supposing that it will hopefully lower people's blood pressure. What would we expect if our drug is working? Right, negative in that case. So as our dosage level goes up, we would expect the blood pressure of patients to go down. So we would expect the slope to be negative if our drug was working as we hoped. And then what about mileage on a car related to the lifespan of a car part, how long it will last? Negative as well, right? So the longer or the more miles we have on the car, the shorter we expect a car component will last. So it's also negative. Yeah. And then lastly, the advertising expenses was our X, and then revenue was our Y. So would we expect this to have a positive or negative relationship here? Yeah, hopefully positive. It'd be really bad if it was negative. Although possible, maybe your ads actually turn people off somehow. Okay. All right, so let's try, for example, to give the assumed simple linear regression model, for example, D. And I think what will be helpful here is to look at the guide for Stat 216 document. Okay. So you can find that on the course schedule, at the bottom of the course schedule. All right. Oh, we have a simple linear regression section. I'll make this a little bigger. Okay, so we have this simple linear regression section, and salute. So we can, copy this part, and this is a blueprint statement of the assumed linear regression model. Okay, so we can copy that and then paste it in here. Okay. So whenever I ask for the assumed simple linear regression model, you can start like this. I would highly recommend starting with this, copying and pasting it. And just like before, you keep this part general. So this top part stays the same for every single problem. What changes is the definition of each term in the model. Okay. So Y in this case, let's see. Example D is the social media advertising. So we have X was the here was our X and Y. So what is the response variable? Well, we said it was the Gotcha. Yeah, sales revenue. Thanks. Keep scrolling past it. So we say yj represents the jth observation of the sales revenue. There you go. Beta naught is the intercept, beta 1 is the slope. So we just keep those general like that. We actually don't update that for any problem. Honestly, when you give the assumed model, you don't have to give these parts. I would say what's most important is defining the x and the y. But if you wanted to be thorough, you can. And then x will say, instead of explanatory predictor variable, we'll say how much was spent on social media advertising. And it's always important to give units of measurement. Okay, was it in dollars or was it in thousands of dollars? The numbers from your estimated model will be very different depending on the units of measurement. Okay, so let's suppose it's just in dollars. This is our statement of our assumed simple linear regression model. That's how we get it. And so, yeah, let's assume that we had data on this. Okay, so we had something that looked like we had revenue, and then we had advertising expenses. Okay, let's just call it like rev and then like that. This is too big. Right. Okay, and then maybe we have oops. Okay, maybe our data looks something like that. And it's probably in like thousands of dollars or something. We're working for a big company. So our data looks like that. We use calculus or just software to get estimates of the betas based on this data set that we have. And then we find that the estimated slope is 2. Okay. So I give a blueprint interpretation here. So we can copy that. Again, I would suggest doing that. Paste this here. And so, yeah, very generally, we have for every 1 unit increase in x, we expect y to increase or decrease by this amount. So let's see how we would update this for any problem. So let's start with 1 unit increase in x. Instead of saying that, how can we say that for this specific problem? Yeah, for every $1 spent on advertising on social media. We expect, and then how would we update this part over here? Yeah, we expect sales revenue to increase or decrease by beta. So what should we say, increase or decrease here? Increase, yeah, because the estimated slope was positive. So for every $1, I think I put the dollar sign on the wrong side. Okay, so for every $1 spent on advertising on social media, we expect sales revenue to increase by, and then what should we put here? $2, yeah. Kind of weird that we say $1, but we put $1. So it's confusing. Okay. So yeah, so that's how we interpret the slope there. So this is important because being able to interpret this value, because your business manager, maybe doesn't like statistics, numbers that much. They just want to know, like, how is our advertising campaign working, our marketing campaign? So this is how you can tell them, like, okay, well, based on the data, we're seeing that for every $1 we spend, we're getting $2 more in revenue. And maybe that will help you evaluate like marketing strategies moving forward. Right? Okay, and yeah, let's further suppose in that marketing example, we get a estimated intercept of 5,000. So here we can copy this blueprint interpretation again. All right. So the expected value of, and then instead of y, we'll say the expected sales revenue in dollars. Or we can just say, as long as we put dollars at the end here, the expected sales revenue given that. And then how could we say this in like everyday words rather than 0? Yeah, given that no money is spent on social media advertising. And here we would say $5,000. Okay. So very likely, even if you don't advertise on social media, it's probably reasonable that you maintain some level of sales, and then just advertising gets you some above that potentially. Right. Okay. I was asking Chat GPT about like examples for this in like marketing, because it's really good at coming up with examples like that, and some other ones, because I have not worked for like a marketing company or anything like that doing analytics. But it gave some other examples of like things people model in these types of scenarios. So like, yeah, the bottom line is revenue typically, but it gave examples of like click-through rate, right? So how often somebody clicks on the ad, or how many people you end up getting to click on it and then come to your site, right? Like, so typically that's an outcome of interest that people are using predictive modeling. And then maybe using that, you would estimate like, okay, how many people who click on the site and go to our website actually end up buying something? You could estimate that then too. and sort of work out how much you expect to make based on having this many more ads, right? So which is like what actually one job I interviewed for at Target was geared at that. They called it artificial intelligence expert or something. Essentially, you were looking at the data for ads to see like what could maximize click rate, get people to click on ads on Target's website. So yeah, sometimes branded is much fancier than it is. I think I wouldn't really call that artificial intelligence, but it's branding, I suppose. Okay, so if we suppose that we have these estimates, we could calculate an expected or predicted sales revenue given an investment of $500. All right, so in that case, let's look at our equation. Okay, so we have, whenever I get a predicted value, I try to write out the equation like this. I think it's helpful to be organized. Also, like on an exam, you can imagine I try to give partial credit. So if you can show the work like this rather than just giving one number, you can get partial credit if it was just like an arithmetic mistake along the way, which happens. Right? But it's tough when, like on an exam, if there's just a number here for like this question, for example, and it's wrong, you know, it's tougher to get partial credit. So always good to show work. So 5,000 plus 2 times 500. Nice round numbers here. Yeah, so what would we get as our expected sales revenue then? Yeah, 6,000. Yeah, that would be one more zero here, and then we can get, and then we got. Yeah, I mean, it's early. Okay. So that's an example of how we could get a predicted value from the output of a linear regression model. Okay. And how we can interpret some of the things, some of the estimates that we get. Right. When fitting this model, okay, and I talked about how software gets estimates for these regression parameters. They're called the intercept and slope. It actually is conditional on some assumptions being true. Like the numbers that we get for those, there's a few different ways you could solve for them. People have these common sets of assumptions that they assume are true for linear regression, which result in unique solutions for these. Okay. And specifically, we need a random sample like always. So this is true for most every model you use in statistics. If you're interested in a population, for example, maybe cars produced by General Motors, right? You need to have a random sample of cars from all General Motors vehicles then. Then getting into the more statistical theory in terms of assumptions. Just like ANOVA, the assumptions for linear regression are pretty much all about the residuals. So we need a normal distribution for the residuals. And importantly, this is not something the central limit theorem can take care of anymore. So I mentioned this for ANOVA. The t-test kind of, the t-test is a linear regression model, but due to other things about it, you can apply the central limit theorem. That does not apply for linear regression. And there is a lot of confusion about that when you search online. But it's definitely the case. You cannot use the central limit theorem for normality. We really need those residuals to be bell-shaped. We need them to be homoscedastic in that they have equal variances across the predicted values. We need the residuals to be independent of the predicted values. So this is a slightly new assumption that we didn't really check for ANOVA. And then also a newer assumption as well. We need that there's a linear relationship between X and Y. Okay. These assumptions have to be true in order to conduct what we call inference of the regression model. So that's referring to like hypothesis testing of the intercept and slope, creating confidence intervals, or we'll look at what are called prediction intervals as well, which are kind of similar to confidence intervals. Those methods of inference rely on these being true. I think it's important to note that, like, I took a data mining class in grad school, and this professor who did a ton of research in like machine learning and predictive modeling, he was always very adamant. He's like, too many people are too picky about linear regression. He's like, you can use it whenever you want. You just can't use the p-values from it if the assumptions are not met. But I thought he had a good point that you can still try to get predictions always, even if these assumptions are not true. You can fit a model, get a predicted value. Doesn't mean it'll be very good, but you can try and see how it performs by evaluating it in different ways. So the assumptions, notably, are just important if you look at p-values or confidence intervals. Okay. All right, so we'll look at a real data set here. On Scrabble letters, which I thought was interesting. One of the other professors thought of this in the department. So Scrabble, it's a game I played as a kid. It's older now. Has anyone played Scrabble before? Okay, great. So a lot of people have. So the letters are worth different point values, right? I think there was like Words with Friends I played for a while too, which is kind of similar. And letters that are harder to use in words because they occur less often in English are worth more points, right? So a Q, for example, is worth 10 points while E is only 1 point because it's much easier to use E in a word when you're spelling it, playing Scrabble. So someone collected the data because there's only 26 letters, and they recorded like the Scrabble point value for the word. And then somehow they looked at like the percent of the time that that letter shows up in English words across like all words in the English language. So A shows up about like 8% of the time. B is only that much. Okay. You can see, so like J hardly ever shows up in words. It's a very uncommon letter, and so it's worth more points. So the idea is like we can use linear regression to describe this relationship between how often the letter shows up in the English language and its Scrabble value. Okay. Two quantitative variables, so we can use linear regression. Yeah, and Z is worth a lot because it's not very commonly showing up in words, right? This is kind of an interesting data set because it's so small, actually, that we can look at the whole thing on the page here. There's only 26 rows. So a linear regression model was fit with SAS, and we obtained all this output, not that output, this output below, which is a little bit small, but we'll zoom in as we look at it. So here's the scatter plot showing the Scrabble point value and then the relative frequency in English writing. All right, let's scroll back up to the first point. Okay. So based on that scatter plot, okay, would we say there's a positive or negative relationship between the two variables? Negative, right? So always just try to imagine like a one straight line that best fits that pattern in the data. It's probably something like this or something similar. Okay, so it has a negative slope, it's sloping downward. And let's think about if that makes sense. So as the letter occurs more often in English writing, the point value is going down, right? So that makes sense. It's always a good to do like a little logic check, make sure the data's coded how you expect it to be. Negative. All right. And then like we were just talking about, does that seem reasonable in this context? So yes, because okay. But note that for linear regression and the correlation coefficient, more specifically, these rely on a linear relationship between x and y. So the correlation coefficient is actually r, which we denote with lowercase r commonly. Is like you can think of it like a standardized slope. So the slope can be any number. It's not bounded at all. It can be negative infinity to positive infinity when it describes a relationship. And it depends on the units of measurement that are used for the problem. So if it's in thousands of dollars or just single dollars, the size of the slope will change. Correlation coefficient is a way to describe the relationship between x and y such that it's standardized to be between -1 and +1 always. Okay. But there's actually a formula that you can calculate the correlation coefficient based on the slope here. So they'll always match each other in terms of size, but the correlation is bounded between -1 and +1. Right. So people like to cite the correlation when describing relationships between variables as well. It relies on all the same assumptions as linear regression. So talking about that here, this is one of the most widely used statistics, the correlation between two variables, x and y. But it's comes with a lot of caveats. So this grid of plots that someone made, I think, illustrates this point really well. Here they gave 16 different data sets with an x on the horizontal axis and a y. These all have a correlation of 0.5, positive 0.5, but they show very different relationships in the data. Okay. So like these top two, it seems not too problematic to use the correlation as a measure of association between x and y. it's a straight line relationship. There's nothing too problematic about the patterns and the points. Okay. Here's where you can get some funny cases. So like in this plot, you have all the points are squished at the left side of it, and then you get one point really far to the right, and that can result in this correlation being 0.5 still. But it's a very different story than these first two plots. Like if you were trying to use X to predict Y here, how would it do in this plot? It would do really bad, right? Like the predictions are all on this straight line. You would see most of the time your predictions would be really bad. But if you don't look at the plot and you just see the correlation, like, oh, it's 0.5. So we'd do pretty well. You would think you're doing decent, which is sadly what happens to people sometimes. But when you plot it, you can see like, oh, our model's not doing a good job. That's not a good model for the data. In a similar story here, where it's just the grouping of the points is shifted to the other side. Here you would think, based on the correlation, that maybe you're doing a good job with your regression model, but when you plot it with a scatter plot, it's like, oh, your predictions are actually really bad. Okay. And so the reason that happens, these are violating the straight line relationship, the linear relationship assumption. So that's why it's important to check that in order to rely on the estimates that you get for your model. Okay. This one's not as bad. Let's see. Yeah, when they say increasing spread here, they're saying there's the fanning that's violating the homoscedasticity assumption. You wouldn't notice this unless you looked at the residual by predicted value plot as much. It's a little bit harder to spot just in the scatter plot of X and Y, but you would see it in those diagnostic plots that we'll look at. Same with this one, where it says it has funneling. Okay. Yeah, this is another example where you have a correlation of 0.5, but that's actually quite misleading. There is a very strong relationship between X and Y here, but it's just nonlinear. It's a quadratic relationship, which again, you wouldn't know unless you plot the data. So that's why it's really important to plot your data. Like in an extreme case, you can have that. So here he's showing like all these plots where X and Y have a correlation of 0.5. You can have this case where it's if X, you have Y, and then okay, if the quadratic pattern is just right, you can actually have this case where you have this type of relationship in the data, but when you fit a straight line, what you would find is like this. And it would say the slope is like 0, correlation is 0. If you just look at those statistics, you would think there's no relationship between X and Y. Okay. But again, when you plot it, what you'd see is like, oh, actually, there's a really strong relationship between X and Y. It's just nonlinear. So this is a huge caveat that I'm really emphasizing here because so many people, this is so often done where the correlation is calculated and it's like not considered if it's actually a straight line relationship or not. So it's actually a really restrictive assumption to say like, oh, they follow a straight line with each other. There's so many things in life that don't necessarily follow that type of pattern, but so it's always important to check. Yeah, here's one where it's it says sinusoid, so it's following like a sine function relationship. Again, where x is actually very predictive of y, but just not in a straight line way. Yeah, there's so many different issues here that this person illustrates in all these plots that are really difficult to spot unless you plot the data. So it's always good to have a scatter plot. Here's a good case of like, you have the points up here, and like, actually, yeah, the slope is correct here. But it looks like there's maybe a grouping variable that should be accounted for. Like maybe you need a separate linear regression within each of these groups because the intercept looks like it's different. Okay. So this is all stuff you wouldn't necessarily notice unless you plotted it. Right. So main takeaway, we should be skeptical of the correlation coefficient unless we see a scatter plot of the data. So what do we think here? Looking at this plot, is this looking like a linear relationship between x and y? No, not really. If we think about like what line best fits this, oops, not like that. It's really hard to draw with the zoom tools. Okay, it's something like that, right? So that's more like quadratic, or just certainly a non-linear relationship here. So this would violate the linear regression assumptions. No, the relationship appears to be non-linear. So that already violates one assumption. So unfortunately, p-values and confidence intervals associated with the regression model are now not valid. Okay. We'll still go through and check the assumptions later just for practice, but another thing actually that's not formally part of the assumptions, but that's something you should check for in a model are what's called influential points and outliers. So influential points, which I kind of explain more, I added a new section to the guide document recently talking about these, but it talks about it in the Introduction to Modern Statistics textbook, the readings in that section. But outliers and influential points are problematic data points for the linear regression model. Let's see, I talk about outliers first. Okay, so influential points have a disproportionate effect on the regression estimates compared to the rest of the data. So they are very influential in that they pull the regression line towards themselves unfairly. They're the squeaky wheel that gets the extra grease. So if you can see it in like these plots up here. Okay, like this single data point over here pulls the regression line all the way over towards it. It's really greedy. And if it weren't there, like you can imagine in this plot, if it weren't there, the regression line maybe would be something like this, because it would fit all these points much better. But what happens is when a point has a really big x value, or it's really far away from the other points x values in the data set, the way the math works out, it has a considerable amount of influence or pull on the regression line. Someone compared it to like a seesaw, which I thought was maybe a good way of describing it. So if like you're in the middle of a seesaw, you don't have as much leverage over pushing it or pulling it either way. But the further you get out towards the edges, you have a lot more leverage. And that's actually what they call it in statistics. Like they say this point has a high leverage. So it's able to pull that point. Okay. So the amount of influence that a point has is something we want to consider, because if points have too much influence, it's ruining the predictions for all the other points, which is not a good thing. And so how do we, yeah, looking at the plots is always a good thing, but people have also come up with numeric summaries to describe like exactly how much influence each point has. And so two of the most commonly used ones are Cook's distance measure, commonly just called Cook's D, which is named after Dennis Cook, who's still a professor in statistics at Minnesota, actually. I studied biostatistics, not statistics, so I didn't get to take him, but he's still there though right now, actually. And then there's DF fits, which is difference in fits. So we'll talk about those measures next time and continue with this activity here.